Okay, good morning, everyone. Welcome to this session on graphs for technical interviews. My name is Omkar. I am the head of curriculum at Interview Kickstart. And over the next 40 or 45 minutes, I'm going to present to you the IK curriculum for graphs. I want to emphasize that this is going to be just a sneak peek, much like browsing a few sample pages of a book on Amazon.com. But we'll be available at the booth, and I'm happy to chat over any of this in more detail with you. So the first point to note is that graph algorithms are crucial to learn in all top-tier company technical interviews. Google, for example, advises all candidates to master graph algorithms using these words. You're supposed to learn about graphs. You need to understand how graphs are represented in memory, and you need to know in depth the basic graph traversal algorithms like breadth-first search and depth-first search. Facebook says the same thing more briefly. They want you to learn about graphs, especially the traversals, BFS and DFS. So does Amazon. Pretty much every top-tier company wants you to master graph algorithms for coding interviews. So that's the bottom line. And graphs are also a relatively hard topic to master. This is an overview of what the graphs curriculum at IK looks like. I have shown the curriculum itself as a graph. You can see that the topics we cover are shown in 3 different colors. The topics in green are the ones that we cover in our foundational material and live class. The topics in blue and gray are more advanced. We cover them in extension classes. So we start a study of graphs by looking at basic graph theory. It turns out that graphs are a topic where it is important to understand some theory. Only then can you build correct algorithms and understand why they are correct and why they are efficient. So the starting point is always basic graph theory, where we cover the basic terminology, concepts, and basic patterns of reasoning about graphs. We don't do this via a dry list of definitions, as typically found in textbooks. Rather, we do this via the real story of the origins of graph theory. Back in the 18th century, in the Prussian Empire, in the city of Königsberg, where in the midst of a booming economy, the residents construct 7 bridges across a river that flows through the heart of the city, shown here in this Google Maps image. You can see the 7 bridges. Every Sunday morning, as the residents took their morning walk, they were curious about the following question. Can one walk across the 7 bridges without crossing the same bridge twice? That is, can one walk across the 7 bridges by crossing each bridge exactly once, without repeating any bridge more than once, and without missing out on any bridge? This question was intriguing enough for them that they took it up with the mayor. The mayor was not a mathematician himself, so he wrote to the most famous mathematician of that time, Leonhard Euler, requesting him to solve the problem. Euler did solve the problem and published the solution to it in a paper. This is his original sketch from the paper showing a subset or a specific section of the map of the city of Königsberg. You can see here that Euler chose to represent the different land regions of the city by using 4 letters. So from Euler's perspective, it was not important what the shape or the size of each of these land regions was. All that was relevant was that there were 4 land regions, A, B, C, and D, and they were connected using 7 bridges. Again, it didn't matter what the length of each bridge was, what the width of each bridge was, where they were located. All that mattered was that there are these 4 land regions connected by these 7 links, and so we can ignore all the other details. Now this diagram, which Euler did not draw himself, but that's how we visually think about it today. This diagram can be shown in a slightly neater way, and it's what we today know as a graph. So a graph is basically a collection of vertices corresponding to the land regions and a collection of edges corresponding to the bridges. Since these bridges were two-way streets, there are no directions on the edges, and so we call this kind of a graph as undirected. Two vertices are said to be adjacent if they are directly connected by a bridge. So C and D are adjacent. A path is just a sequence of adjacent vertices, so D, B, A, C is a path. A cycle is just a path that ends at the same vertex from where it starts. So effectively, modeling the map of Königsberg as a simple graph like this, the problem that Euler had to solve was, is there a path in the graph that visits every edge exactly once, without missing out on any edge, and without repeating the same edge more than once? And this is the well-known Eulerian path problem. Euler's answer for the specific graph corresponding to the city of Königsberg was no. You can't take a morning walk in that way. But Euler actually ends up solving the problem for a general graph. And Euler's analysis of that is what we cover in our foundation material. We go over it. It takes more than an hour. I won't be able to do it here, but I'm happy to do it at the booth if any of you is interested later. It also turns out that one of the popular interview questions at Uber and Facebook requires you to understand that analysis. And again, I can tell you what that question is and how you would go about solving it later. So there are three broad lessons that we learn from going through that kind of analysis. The first lesson is in problem solving. Given a question that you haven't seen before, and a question for which you have no idea what method to use to solve it. Remember that there were no graphs in Euler's time. He had to pretty much come up with a new way of looking at things from scratch. How do you go about solving these kinds of questions? So Euler's analysis provides us useful tips in problem solving. The second lesson we derive from that analysis is, how do you take a given real-world problem or an interview problem in which you're given a set of objects and model it as a graph? When do you model it as a graph? The important signal is the presence of pairwise relationships between the vertices, which point you to thinking in the direction of modeling the given set of objects as vertices of a graph and these pairwise relationships as edges. The third lesson is that it is relatively hard to invent a new graph algorithm from scratch. So if we want to model a given interview problem as a graph problem, you have to simultaneously think about which standard graph algorithm you will use once you have modeled it. And very often, that standard graph algorithm will affect the details of how exactly you model it. The different standard graph algorithms are what we cover in our curriculum. They're all shown here. But of course, we first need to understand how graphs are represented in memory. And when we talk about representing graphs in memory, we are really talking about representing edges of the graph in memory. The vertices can be maintained separately using the more simpler techniques like dictionaries and sets that are typically covered in the data structures and algorithms part before we even come to graphs. So the popular ways of representing edges are adjacency lists, adjacency maps, and adjacency matrices. So if you are given a graph with these 10 vertices, notice that their names are digits instead of letters here. An adjacency list is basically a list of neighbors for each vertex. So if I want to find out what are the neighbors of vertex 0, I notice that the neighbors are vertex 1, 6, and 8 here. And so I go to the adjacency list for vertex 0, and it tells me what are the neighbors of vertex 0. An adjacency matrix on the same graph would be in the form of a 10 by 10 matrix where row I, column j is a 1 if vertex I and vertex j have a direct link between them in the original graph, and it would be 0 otherwise. If there's no link, it would be a 0. Now, it turns out that adjacency lists and adjacency maps are just a variation of adjacency lists where the neighbors are stored not in the form of a list, but in the form of hash tables. These two are the most useful when it comes to graph algorithms. They can help us answer the following two questions very fast. Given a particular vertex u, what are the neighbors of u? What are the direct neighbors? Which vertices does it have a direct relationship with? So in this example here, you can see that the neighbors are v and w. Another question that could be asked in the course of coming up with an algorithm on graphs would be, given two vertices u and v, is there a direct edge linking them? Adjacency maps are extremely useful in answering this question really fast. Now, these two questions can be extended to ask about long-distance relationships or indirect relationships. Given a vertex S, what are the long-distance neighbors of S? Which other vertices does it have an indirect relationship with? And given two vertices S and V, is there a long-distance relationship between them in the graph? To answer either of these questions, we can't directly look up an adjacency list or an adjacency map. We need to find a way to start exploring the graph from the given vertex S, and discover all reachable vertices from S. And that requires an exploration or a traversal of the graph. Now, even students of computer science often miss the fact that all the standard graph algorithms that you see here are essentially minor variations of a general graph traversal algorithm. If you understand this general graph traversal algorithm, you're on your way to understanding all 6 of them in one shot. What is that general graph traversal algorithm? I'll be going over that next. Are there any questions so far? Okay. So let's take an example of a directed graph here. So you can see here that this small graph here has directions on the edges. So think of them as one-way streets. Given this directed graph, which vertices are reachable from vertex 1? Let's say we want to answer this question. You can see by a visual inspection of this graph that you can't reach this isolated vertex 6 over here, and you can't reach this vertex 7 on the left. But this graph could, in theory, be thousands or tens of thousands of vertices big. And so we want to find out how would we get a machine to figure out the answer to such a question. What we do is we visualize all the vertices of this graph initially as unreachable vertices, undiscovered vertices. They are like fish swimming deep inside an ocean. And that's what you see here on the right side. But we are given in this problem that there is a starting vertex. We know where to start from, and that's vertex 1. This is our source for the exploration of the graph. So since we know what this vertex is, we pretend that we have caught it inside a fishing net, we have trapped it, or we have put it inside a bag. Having done so, we drag it ashore. We take it out of the bag and we drag that fish ashore. Now, we know what other fish or what other vertices this particular vertex has a direct relationship with. You can see from the graph here that 1 has an outgoing edge to 2 and to 5. And so we are able to reach out to those immediate neighbors of 1 and put them into the bag, because we now know that these vertices are reachable. So effectively, once we figure out that a vertex is reachable, we put it into the bag. And then in each step, we make a choice about which fish do we next want to pull out of that bag. For the purpose of this example, I'm making these choices arbitrarily. So let's say we decide to take vertex 2 out of the bag next by pulling on this edge. So you can imagine dragging this vertex out by pulling on this edge. And that's where it lands. So we now have vertex 5 left in the bag. But when we look at this fish that we pulled ashore, we again see that there are other fish it has a direct relationship with. So vertex 2 has an outgoing edge to vertex 3 and to 4. And so those are the 2 new fish that we have discovered. We put them into the bag, and then we repeat the same process. We decide which vertex do we want to pull on next. We make that choice arbitrarily for now. We decide to pull on this edge from 2 to 4 to drag vertex 4 ashore. And that's what we get. This time, vertex 4 only has one neighbor, outgoing neighbor, vertex 5, which is already in the bag. So there are no new fish added to our bag. We keep going. We make an arbitrary choice here. Let's say we decide to drag 5 ashore by pulling on this edge. Again, 5 has no new outgoing neighbors that we discover. And so we have only one choice left at this point, which is to drag this vertex 3 ashore. And once we do that, we see that there are no fish we can now reach out to. Our bag is empty. And what that means is, what we have on the left are the set of vertices that are reachable from our source vertex, vertex 1. So this is the result of this general graph exploration. We got a search tree on the left at the end, which had the source vertex as the root. That's vertex 1 over here. And the vertices in this search tree are precisely the set of vertices or nodes that were reachable from the source vertex in the original graph. And in general, if we decided to drag a vertex C ashore by pulling on an edge from vertex P to it, then P becomes a parent of C in the search tree. So when we dragged vertex 3 ashore, we pulled on the edge from 2 to 3, and so vertex 3 becomes a child of vertex 2 in the search tree. So we can visualize this graph exploration more concretely now as in the form of pseudocode. So we want to write a general function which will explore a graph starting from a source vertex S. Initially, we know that all the vertices are undiscovered. They're free-floating, free-swimming fish in the ocean. What we did at the beginning was we initialized an empty bag and we put S in it. At least we were given the source vertex S. We mark it as discovered. Right? Every vertex that enters the bag is marked as reachable or discovered. And then, as long as we have some vertex in the bag, what we did is we picked an arbitrary vertex, we reached out to all its direct neighbors, we checked if any of them were undiscovered yet. If so, we added them to the bag, and then we repeated this process. We marked them as discovered, and we repeated this process. So if we fast forward this algorithm to a general point in the execution of this exploration, we will have a bunch of vertices on the left, which would of course include the source vertex and also other vertices, a bunch of other vertices lying in our bag, and a bunch of other vertices that have not yet been discovered. At each step, what we are doing is we are choosing some vertex U from the bag to pull out. We drag it out by pulling on an edge from one of the vertices that are ashore, leading up to that vertex U. Now this vertex P is going to become the parent of U once U is dragged ashore. And the assumption, of course, is that each of these vertices is already connected to the source vertex as part of a growing search tree. Then we can visualize U as becoming part of the search tree with a well-defined unique path from the source vertex leading up to U. And what do we do when we drag U ashore? We reach out to its direct neighbors. We check if any of them still lies undiscovered in the ocean. In this case, vertices V and W are undiscovered, and so we add them to the bag. Okay, so if any of the neighbors is undiscovered, we put the neighbor in the bag and we mark it as discovered. Right.
Would you mean bag, do you mean a set, or do you mean it would be a data structure that would be maintained?
So it would be a data structure. I will come to that shortly. All the different graph algorithms are using different data structures for implementing this bag. And they all have different policies for which vertex you will next pull out from the bag. So this is the common theme across all graph algorithms, traversal algorithms. Each vertex has a life cycle. It starts out deep inside the ocean, undiscovered. At some point, it is discovered. Right? How is it discovered? There is another vertex that's dragged ashore with which it has a direct relationship. And so at that point, it gets added to the bag. And then at a future point, it's going to be pulled out from the bag. Right? There'll come a point when it's pulled out of the bag and moved into the search tree on the left. And this continues until the bag is empty. So coming now to your question, all the standard graph traversal algorithms are just variations of this general graph traversal technique. If we decide to use a first in, first out queue to store the vertices, the specific graph traversal algorithm we end up with is breadth first search, where there is a well-defined policy that the next vertex that is going to be pulled out of the bag is the vertex that was added the first to the bag. If we use a last in, first out stack to maintain the collection of vertices, then the specific graph traversal algorithm that this becomes is depth first search, where the vertex that we're going to pull out next was the one that was added most recently to the bag. If we use a priority queue to maintain the collection of vertices, then each vertex is going to be inserted into that collection with some priority value. And the next vertex that's going to be pulled out from the bag is going to be the one with the highest value for that priority. And depending on how we define that priority, we get either Dijkstra's algorithm for computing shortest paths in a weighted graph, or Prim's algorithm for computing the minimum spanning tree in an undirected graph, or the best first or A star algorithm, again for computing shortest paths. So all of these standard graph algorithms are essentially variations of this general graph traversal algorithm. I don't have time to go into any of them in detail. This is just a sneak peek. I'm happy to discuss them with you in more detail at our booth. But in our curriculum, we specifically focus on BFS and DFS next, because recall from what I showed you at the beginning, that is what gets asked most frequently in interviews. So we look at all the popular applications of BFS and DFS on both directed and undirected graphs. And then in our extension classes, we look at more advanced applications as well as these other algorithms. So I want to finish off by walking you through a sample interview problem. This is the flood fill problem. The problem is essentially the following. you are given an image in the form of a two-dimensional array of pixels where each pixel is represented by an integer value, and the integer value denotes the color of that pixel. You're also given the coordinates of a starting pixel. So that happens to be this particular pixel here. Now this pixel is initially white in color, but you're given the value of the new color that this pixel should take, and in fact all pixels that are connected to this pixel having the same color, the same starting color as that pixel, all of those cells need to be changed to green. So that's called the flood fill operation. You're supposed to modify the two-dimensional array to flood fill it. And this corresponds to our popular application like Paint, where you pick a particular color, you tap at a particular location in your image, and every single pixel that is reachable from that starting pixel is changed to that new color. And so when that is done on this sample two-dimensional array, this is the result of the flood fill. So based on what we have discussed, do you have any thoughts on how we would go about solving this problem? Yeah.
You start from the starting point, iterate the neighbors, then you can choose either BFS or DFS.
Right.
BFS would be the most natural to add all the neighbors, direct neighbors, into a queue, color the current cell that I'm on, and then repeat this process until the queue is empty.
Right. So when we teach our candidates graphs, we first ask them to recognize that this is a graph problem, and that involves recognizing that what you're given is basically a two-dimensional collection of objects, and there are pairwise relationships that are defined on those objects. And those pairwise relationships are these spatial neighboring relationships. So this might be a graph problem, but then to be sure, we don't want to immediately model it as a graph. We also want to figure out simultaneously which standard graph algorithm we would use. So the starting vertex here would be our source vertex in exploring the graph, and we can see that to flood fill this image, what we need to do is we need to figure out which vertices are reachable from the source vertex with the same color as the source vertex. So even though this vertex is right next to the source vertex, we don't consider this a neighbor because it's black in color. So we want to explore the graph starting from the source vertex, reaching out to the neighbors which have the right color, and color each vertex green. So this can be done using any graph traversal algorithm, because this is a general traversal algorithm. You could use BFS, you could use DFS, you could also use Prim's algorithm, you could use Dijkstra's algorithm. It seems silly to use them here, but in theory you could. They just happen to be more expensive than BFS or DFS, which is one of the reasons you wouldn't use them. But you're right, we would use either BFS or DFS because both of them work in linear time, linear in the size of the graph. So we can, let's say, pick BFS for this exercise. You could also have picked DFS. This general algorithm is now going to be specialized to become BFS instead of a general search. Right? We start from the given vertex as before. I'm going to keep toggling between these two slides to show you the, how this general algorithm becomes specialized when we do BFS. Instead of initializing an empty bag and putting S in it, we specifically pick a queue, a first in, first out queue, and put S in it. Instead of marking the source vertex as discovered, we paint it green. We paint it with the new color. That is our way of saying that this vertex is discovered. While the bag is not empty, or while the queue is not empty, we are going to pull out one of the vertices. Let's say that vertex is U. And because we are doing BFS, there is a well-defined policy for which vertex is going to be pulled out next. It's dictated by the fact that the collection is a queue, which means the first vertex that went into the queue is going to be the one that's pulled out. So we pop that vertex from the queue, and then we look at all the direct neighbors of U. So we iterate over all the neighbors of U. This could be looking at all the neighbors in an explicit adjacency list, but it turns out that for graphs that are grids, you don't need an explicit adjacency list. If you know the coordinates or location of a vertex, you know what its neighbors are. You can just calculate them by using the coordinates of that vertex, right? If you know that this vertex is in row X, column Y, you know that the 4 neighbors are going to be the vertices in, at x plus 1 comma y, x comma y plus 1, x minus 1 comma y, and x comma y minus 1. As long as these coordinates fall within the legal boundaries of the grid, they're all valid neighbors. So you look at all the neighbors. If the neighbor was undiscovered, that is, if it had the old color, white in our example, what do? We add the neighbor to the bag and mark it as discovered. We add the neighbor to the queue and color it with the new color. And at the end of this, of running this general search algorithm starting from the given source vertex, let's say the coordinates of that source vertex are Sx and Sy, the image should have been transformed, should have been flood filled, and so we return it. So I'm assuming that grid here is the name of that 2-dimensional array. That was the input to our procedure. And so when we do that, we have correctly solved the problem. We could have used depth first search instead of BFS. That would just mean using a stack instead of a queue. So we do have to worry in some cases about edge, special edge cases. These are specific examples of input that might break your algorithm. It turns out that if you're given a new color which happens to coincide with the old color, and if you implement it the way we just saw, your algorithm will go into an infinite loop because it will keep discovering vertices with the old color and keep painting them with that same color. And so edge cases are something that we often teach our students to, how to think about them. So this has to be handled separately. And as I already mentioned, if the queue was replaced by a stack, the algorithm would continue to work correctly. If it was replaced by a priority queue and you add some default priority to it, could be anything, it would still work correctly, although that would be an unusual way to solve this problem. So this was a rapid walkthrough through a single problem, but I'm happy to walk you through different popular graph interview questions and specifically to show you how we use BFS and DFS to solve them. I didn't actually go into BFS and DFS at all. Why is it that we use a queue for BFS? How exactly do we start thinking about BFS? The way we start thinking about BFS is we want to explore the graph starting from a source vertex S in increasing order of hop distance from the source vertex S. So if you imagine the source vertex as the source of an infection, and you imagine the infection spreading out one day at a time, one hop at a time, then eventually all the vertices that are reachable from the source vertex S are going to get sick. And the day on which they fall sick will be the day corresponding exactly to the shortest path distance from the source vertex S to each of those vertices. So we can go through that in more detail. Why is it that to get this desired behavior, we use a first in, first out queue? These are not obvious questions. You need time to go through them, and that's what we do in our foundation material in live classes. So, two broad key findings that we have from our teaching of graphs is by learning these underlying common patterns, a sample of which I showed you, the general graph traversal algorithm, you can learn these graph algorithms faster and in a more efficient way, and in a way that will help you retain them in your mind for a longer time, because instead of memorizing 6 separate algorithms, you are understanding one single way to traverse a general graph. Also, by using common coding patterns for the general graph traversal algorithm and then editing it to create the code for the different standard graph traversal algorithms and keeping that coding pattern in your mind, you can write code for a new interview question that is likely to run the first time. Since an interview is a time test, you need to be able to solve the problem, model it correctly as a graph, use the correct graph algorithm that is needed, but also to code it up fast. And by reusing the code or by using a common template across these different problems, we keep reinforcing those patterns so that when you write the code for the first time, it's going to run, and it will hopefully require only a few edits from the template that is already in your mind. So that, in summary, is our approach to graphs. Happy to talk about it in more detail at our booth.
Questions? Questions? No questions?
I have a question more so about Interview Kickstart. Do you guys just offer just like one program, or do you offer like a subsection of the program? Say, for instance, if you're weak on graphs or dynamic programming, do you offer like a certain course, or is it just one program?
Soham can answer that.
For algorithms, it's a single program. Just graphs, just dynamic programming, very difficult to operationally sustain across sort of different needs. Best thing potentially for anybody who has Interview Kickstart questions, either come visit us at the booth and or attend one of our info sessions tonight. We have one at 5:30 or 5 o'clock, right? 5:30. We do like 3 a week as well. Here, if we can ask restrict questions to graphs, that would be awesome.
Yeah, so great presentation, Omkar. Could you share if there are any quick gotchas or slip-ups when trying to identify a problem as a graph problem? Like the flood fill, I was thinking I could use a matrix and just scan, points on the matrix. So what's a good way to identify a graph problem, and what are some ways people mess it up and go in a different way?
So one common way to mess it up is you can be given an interview problem that has a grid. So you might think of a graph, of modeling it as a graph, but if the problem requires you to repeat the same cell over and over, for example, if it asks you to enumerate all the paths from the source vertex to some other vertex, the different paths will go through different sets of vertices, and many times there could be some paths that also repeat vertices. So the property of BFS, DFS, and this general graph traversal algorithm is they only visit each vertex exactly once. So there are interview problems where you need to visit the same vertex multiple times. And if you try to use BFS and DFS or the other algorithms for that, then that can lead you to go astray. So that's why it's important when you think of modeling something as a graph, you should be able to cleanly use one of the graph algorithms as a black box into which you'll just plug in the graph, the modeled graph as an input. If you see some difficulty in plugging it in, it could be a sign that you're not doing the modeling correctly, or it could be a sign that it's not really a graph problem. So modeling it as a graph is not going to help you.
Good question.
A question that popped into my mind was immutability when you're dealing with graphs. Sometimes you'll have, you're adding, say, a discovered property onto a node as you're going through. And I'm just thinking if you happen to use the same graph twice, you may have a discovered node on it already from a previous iteration. Is immutability something that we think about when doing these problems, or am I just making this too complex?
Well, if you need to maintain, so many interview problems require you to store more information with each vertex. Apart from the fact that they are discovered, you might want to store which is the parent, like which vertex captured, dragged ashore one of these vertices. You might want to store the length of the shortest path from the source to each vertex. So all that associated information follows the same template. You just need to add extra arrays. So instead of a discovered array that's initialized to false, and then it, you keep turning the vertices, the discovered values to be true as you discover more and more vertices, you have more arrays representing shortest path distances, parents, and so on, and you just use them. So you just need to use a little extra space, but nothing else changes.
Hi, thanks for a fun presentation. One of the challenges that occurs in kind of a real-world situation with graph problems, especially with large graphs, is memory explosion.
Right.
And do you have any insights or approaches that you can share where you can either limit or limit the amount of memory that's consumed, or to make it like a constant memory solution?
So there are some variations of graph of these kinds of problems where you can't fit all the edges into the memory. So you see the edges one at a time. And for that, we actually have to use a different kind of data structure called a union find data structure, which is a popular topic in interviews. So we don't cover graph databases or graphs that don't fit, that have to be stored on disk. But this particular variation, where the edges are not fitting in memory, you can see only a few of them at a time, that requires a different strategy and a different data structure, a union find. It's called a union find data structure. So Kruskal's algorithm here uses that. So it's part of our advanced material. We can talk more about it at the booth if you
Though union find is a pretty popular thing at some companies these days. It lasts, I would say, about a year or so, year and a half or so. Union find, we have started to see it as well.
Okay, so I think we're out of time. So happy to continue discussing more at our booth.
We still have a little bit, I think.
Isn't it past 10?
It's 10:15, 9:15 to 10:15.
Oh, okay,
so
okay, sure.
we have enough time. Enough time. If you have questions, feel free.
What is the order of time of it?
So I don't have it on the slides, but I'm happy to explain it in more detail at our booth. Roughly speaking, both BFS and DFS visit every vertex and look at every edge of the graph once. So going back to this life cycle of a vertex, right? Each vertex is discovered at most once. It's added to the bag. Adding a vertex to a bag, whether it's a queue or a stack, is a constant time operation. Extracting it from that queue or stack is also a constant time operation. After extracting it, looking at all of its outgoing neighbors takes time that is proportional to the degree of that vertex. Basically a term for how many neighbors that vertex has. So we might have to look at the adjacency list for that vertex and see what are the other vertices that are directly linked to it, which of them is undiscovered. Finding that out takes a constant time for each of those neighbors because we just have an array with discovered values initialized to false, and if the value is true, that means they've already been discovered previously. So effectively, if you add up the total amount of work you're doing across the execution of the algorithm, it's a constant time for each vertex, right? For the time required to add it to the bag, the time required to take it out from the bag. If you add up that part of the work across all the vertices, that would be order V. If you add up the work that's required to look at the outgoing neighbors of each of those vertices, that's going to add up to a value that is the summation of the degree of all the vertices in the graph. And one of the things that we go through as part of our basic graph theory module is Euler himself says that when you take the summation of the degrees of all the vertices in an undirected graph, it's always going to add up to twice the total number of edges. In a directed graph, it would be slightly different, but in an undirected graph, you're basically looking at each edge from both of its endpoints in the course of exploring the graph. So each edge is touched 2 times, and so when you add up the total amount of work being done for each vertex in looking at the neighbors of each vertex, that total amount of work is going to be exactly equal or proportional to twice the number of edges. And so we add that extra 2e term to the complexity, so order V from before, order 2e from the edges. Order 2e is asymptotically the same as order E. So order V plus E is how we characterize the complexity of both BFS and DFS. It's different for the other algorithms because inserting and deleting items from a priority queue cannot be done in constant time.
In the past, I saw get neighbors implementation that takes all 8 nodes. Why do you only consider 4 neighbors, not the diagonal ones?
So some problems do have 8 neighbors, but these grid problems typically have 4 neighbors. So that would usually be specified in the question itself. If it's not specified, it is important to ask that clarification from the interviewer.
Does it change the algorithm significantly if it is 8 neighbors?
No, it just means
Right.
there are more, the degree of each vertex would be potentially 8 instead of 4, that's all. It would make a constant factor change, but doesn't change the asymptotic complexity.
Yep.
So since DFS is LIFO, we basically don't need any data structure. We can just, right? We don't need to store anything.
Well, are you referring to the recursive implementation of DFS? Yeah, in the recursive, so if you don't use an explicit stack, you could, in fact, you should implement DFS using recursive code. That code is actually very simple, much simpler than this. But there is implicit stack space there. So you are basically storing a chain of vertices implicitly on the call stack while you are, even though you are at particular vertex, there is implicit stack space. Yeah.
How do things change if the connectivity is changing dynamically?
So that is one of the examples where union find is used, when edges are being changed dynamically. Particularly adding, so edges are getting added dynamically. Normally, all these algorithms work on static graph inputs. So it's very uncommon to find except apart from union find, I haven't seen many questions where the graph itself is dynamically changing.
Oh, no more questions? Questions, please. Still have 5 minutes.
Problems like isomorphism type of things?
No, we don't do them because they're not typically asked in interviews. So he asked about graph isomorphism. I mean, there are more advanced algorithms that you would typically study when you do a course on graph theory. But these are the ones that we do cover. And within this, a popular application of DFS is in doing a topological sort. Basically, instead of sorting a bunch of objects based on their values, you're sorting these objects based on these relationship arcs. So you sort the vertices in a way that all the relationship arcs are running from left to right. So we're talking about directed graphs here. And then topological sort is then further extended to other applications, like finding the longest path in an acyclic graph, finding the shortest path in an acyclic graph, finding the number of paths in an acyclic graph, finding the strongly connected components of a directed graph, finding bridges and articulation points in an undirected graph. So those are some of the extensions that we discuss for DFS. We generally do this, we don't cover this as part of the first 2 months, just because we want to understand how these algorithms are designed from scratch. We don't want to just remember their names. So Dijkstra and Prim are good examples of greedy algorithms. Best first, A star, add something called branch and bound. Bellman, Ford, Floyd, Warshall, they use dynamic programming. And so it's important to first understand these different optimization techniques like dynamic programming, greedy strategy, branch and bound, before applying them on more complex types of inputs like graphs. So our approach is to also try to understand how these algorithms were designed in the first place, just like Euler designed the very first example of a graph and a solution to that problem. So that's the reason we divide up this material into 3 different sections. We don't cover it all in one shot.
Do you have recommendations on some web resources to find examples of graph being used in real life? So it helps us build an understanding of how, if you just study the computer science of it, it's hard to model it.
Yeah, so there is, Steven Skinner has a popular book, The Algorithms Design Manual, in which he goes through a number of applications of graphs in real life. So that would be a good resource. Is it available online for free? I'm not sure, but it has been traditionally a very popular resource for interview prep. Steven Skinner, he's a professor at, I think, SUNY Stony Brook. Skiena. In fact, many of the lead code problems and other resources that people use, many of those problems originated from some exercise or problem in, at the end of some chapter in an algorithms textbook. So I personally like to use an algorithm design and analysis approach to parse through these problems instead of solving them in a random order, because that way you get to group together questions which belong to the same thought pattern and coding pattern.
More questions? We are right at the time also. Well, thank you, everyone. Thank you, Omkar, very much. I hope